So many of you remember the symbol for the integral, but we need to back up and recall where that came from. All right, so yesterday we reviewed how the area is approximated by a series of base times heights if we're doing just rectangles. So it would be base times height 1 plus base times height 2 plus base times height 3, dot, 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 until we get to base times height n. Now that's cumbersome, so we come up with a way of simplifying that and writing it a little bit more elegantly. And so we can say, all right, well then we'll say that the area is approximated by the sum, because the sum can represent all of that addition over and over and over again, of b h sub k, as k, and so when you write summation, you put the first one on the bottom. So what did that subscript start with? 1. And then what did the subscript end with? N, and so we put that at the top. So that's another way to write that a little bit more elegantly. That is the sum of the constant base times all of those different varying heights as the subscript goes from 1 to n. And what would we like n to be in an ideal world? We would. We'd like n to be infinity. And so then we write, so the area is approximated by the limit of the sigma as k goes from 1 to n of b h. Actually, I'm going to switch it around. You'll see why in just a second. I'm going to do h sub k times b. And as n then approaches infinity, because as we approach infinite many rectangles, we will increase our accuracy over and over and over again. Okay, all right, so now how did that become an integral? So let's think about this one very, very skinny rectangle. Right now we're calling the base b, and we're calling the height h sub k. How do you know how tall all the rectangles are? Okay, it's the y of the function. So instead of calling it h sub k, let's call it f of x sub k, which is the same thing. Okay, and then b, the base. The base is consistent the whole time. How big is this base? Small. Very small, right? Okay, infinitesimally small. This base is extremely small. And the base is sitting on the x-axis, and it's the same distance all the time, but it's very, very small. And so we have seen Leibniz write that as dx. That's the differential of x. Differentials are very, very small things. So small that they are approaching 0. So then let's go back to our equation. So now we've got the area is approximated by the limit as n approaches infinity of the sigma as k goes from 1 to n. And then of h of k, we use f of x sub k. And for b, we use dx. This is where Leibniz really took calculus to a whole new level. Newton focused so much on the physics of it and his prime notation. Leibniz used his differential notation, and he is the one who came up with something to replace all of that. I mean, literally, I probably would get sick of writing that over and over and over again. And so he created, literally made up, the new symbol called the integral. That single symbol represents all of the other stuff. It represents the fact that the limit's approaching infinity. It represents the fact that we have a summation of infinitely many rectangles. And so it is f of x sub k dx. And gradually we just drop the sub k. We don't need that anymore. But the area is determined by the integral of f of x dx. And so we can drop that subscript now. We don't need that anymore because there's no k's. And then to specify the integral, then we've got a's and b's as our beginning and ending term. And that's where the integral came from. But the meaning of the integral is the limit. And so I have seen multiple choice questions that look like this. Okay? Evaluate blank. And you're looking at it and you're like, crap, it's got this sigma and blah, 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 it's terrible. And they really don't, they just want you to change it to an integral and then do the integral. They're not meaning for it to be super complicated. Only if you're going to share with everyone in the class may you open those Swedish fish. Okay, pass it around.
I will let you guys can take as many as you want, like, honestly.
All right. So what you're going to do, again, it just really bugs me that like volleyball players can eat like crap on the day of a match. And like cross-country runners have to start eating good like 3 days beforehand.
I can eat candy for soccer too. Yeah.
Okay, well, if you guys don't play good today against Village, we're going to say, that's all that crap you ate.
Oh my. I can take a couple of those, yeah.
All right.
Yeah. There you go.
All right, so here we go. Evaluate. The limit as n approaches infinity of the sigma as k goes from 1 to n of the square root of 4 minus x squared dx. Right? And you look at that and you're like, okay, that just looks horrific. Right.
I'm not going to try to.
Okay, on 0 to 2. So that means infinitely many rectangles all squeezed in underneath that little graph. Okay, well, first of all, we're going to turn this into an integral. So it's going to be the integral from 0 to 2 of the function 4 minus square root of 4 minus x dx. After we turn it into an integral, we're going to turn it into a geometry problem. Okay, because there is no need for us to stress out about doing calculus here. This is a geometry problem. What does the square root of 4 minus x squared look like? It's the top half of a semicircle. Okay, it's the top half of a semicircle. So the function itself looks like this, with a radius of how much? 2. My bounds are limiting me to 0 to 2. So this is just a simple geometry problem. This is a quarter circle. Why is it not a parabola? Because of the square. The square root and the square combination. If it had the square root, makes it not a parabola. If it was a parabola, it would be 4 minus x squared.
Doesn't it become like...
Let me show you. Let me finish this sec. Okay, 1/4 pi times the radius of 2 squared. So the answer is pi. So you're not going to do actually any calculus tonight at all. Okay, it's all going to be understanding the integral and then turning it into a geometry problem. Okay, 6.3 is where the calculus actually starts. Okay, all right. All right, evaluate. I'm just going to give it to you in integral forms from -2 to 5 of 7x with respect to the x-axis. By the way, if they ever say dy, then everything is going to be shaded to the y-axis. You've got to find the geometry that way. All right, so we're going to just draw this. So 7x. 7x is a oblique line with slope 7. Going from -2 to 5. So -2, 1, 2, 3, 4, 5. And so I'm going to have a triangular piece up to the origin, and then a larger triangular piece on the other side. Okay. All right. We're going to use symmetry to help me out here. Because the triangular piece that's under the x-axis has what kind of area? Negative. And so a couple ways you could do that. You could just separate this into a negative section and a positive section. That would be one way. Another way is to subdivide this using symmetry. You could say, okay, well, what if there was a line 2 here? Then I would have a triangle here that would cancel out a triangle right there. And so then you could just totally cancel those two out. And then what shape are you left with? A trapezoid. So it doesn't matter to me if you want to do a positive triangle and negative triangle, or if you want to change it to a trapezoid. And the trapezoid would just go from 2 to 5. So this would be the same as just going from 2 to 5 of 7x dx. And so that's going to be a trapezoid. And that trapezoid is 1/2 of the height on the left, which is 14, plus the trapezoidal height on the right, which is 35, times the base, which is 3. And so you can evaluate it that way. That'll be 49 times 3 over 2. Okay, any questions about that? Okay. All right. I'm going to give you a geometric value that you can use in other equations now. It's a trig one. All right, given from 0 to pi of sine of x dx. So in geometry, that is the first arch of the sine curve. And it's the area from 0 to pi. I'm going to give you that constant value that has a constant. Does anybody remember what it is from last year? No, it is 2. Now, you could prove it, but what are you going to need to be able to prove that? You're going to need calculus to prove it, okay? So right now we're just going to go with that's a fact. Therefore, half of that should be 1. So using that, you can figure out just about any sine or cosine integral, whether it's shifted or flipped or reflected. You'll just use the geometry of how much a full shape is worth. And so given that, you might be asked to find then, what is it from 0 to pi of cosine? So then you're going to draw the cosine graph, which looks like this. And you can use geometry to know that the top part is equal to half of what the other one was, and the bottom part is negative. And so we're looking at 1 minus 1, so a net total area of 0. Okay, I know that this shape right here in the sine graph is the exact same as this shape right here. They're the same size.
I was like, I thought we were supposed to find sine.
No, I told you that it was 2. Yeah, sine of x is already given to us as 2, and so half of that would be 1. All right, so either all of the geometry will be regular shapes or predictable shapes, or you're going to get geometric shapes that you don't know, and then you can do Math 9 on your calculator. So here's an example of a Math 9 situation. All right, so find the area under the curve e to the negative x squared on the interval 0 to 5. That is not a geometrically approved shape. It's not a circle or a trapezoid or a triangle. So what you have to do is write the appropriate integral and then use f and int to evaluate the answer. So part of the grading is, did you write the integral? So if it's a 2-point question and all you write is the value, then you don't write the integral, then you only get half the points for that. So you would set up 0 to 5 of e to the negative x squared dx. So 1 point for writing the integral, and then 1 point for evaluating that using f and int, so math 9 on your calculator.